Today we'll talk about constraint propagation, another very general purpose method. Constraint propagation is a mechanism of inference where the agent assigns values to variables to satisfy certain conditions called constraints. It is a very common method in knowledge-based AI under a number of different topics such as planning, understanding, natural language processing, visual-spatial reasoning. Today, we'll start with defining constraint propagation. Then we'll see how it helps agents make sense of the world around it. Our examples will come mostly from understanding natural language sentences as well as visual scenes. Finally, we'll talk about some advanced issues in constraint propagation. To illustrate the technique of constraint propagation, let us consider this figure drawn on a 2D surface. Although this figure has been drawn on a 2D surface, you and I can almost immediately recognize that this is a 3D cube. How did we recognize that this is a 3D cube? How can we help machines do it? Cube is an example of a trihedral object. A trihedral object is one where three surfaces join at a particular point, at this particular point. In general, one can have polyhedral surfaces. A polyhedral surface is one where multiple surfaces join at the same point. So a soccer ball with its white and black patches is an example of a polyhedral object because at one point several surfaces can join. A pyramid is another good example of a polyhedral object. A pyramid has four surfaces joining at the apex. So let's do a simple exercise together. Here are 6 figures all drawn on a 2D surface. Which of these 6 figures do you think represents a 3D object? What do you think, David?
So I said that 4 of them could represent a 3D object. This could be a cylinder, this is some kind of trapezoidal prism, and this looks kind of like a pyramid from above with the top lopped off. We can either see this as looking down at some kind of pyramid, or we might also see this as looking into a box. This one's a bit of an interesting example. It doesn't as naturally lend itself to interpretation as a 3D figure, but at the same time, we can imagine that that's what you would get if you looked at this figure directly down.
David, it is interesting that you did not pick this as an answer as well. I guess I would have picked that one. I see this as an x-axis, the y-axis, and the z-axis, and because all 3 axes can be identified here, I would have thought that this too is an example of a 3D object.
That's interesting, Ashok. Now that you mention it, I can't stop seeing it as a 3D object. Now I see it as kind of a folded piece of paper that just has a line drawn up the center. Initially, I don't think I looked at that as a 3D object because I saw the lines as having to represent places where the figure folded or where different planes met. But if we look at the line at the middle as just kind of something drawn on the figure, it immediately pops out as a 3D object for me.
And this brings us to the point of this exercise. The point of the exercise is that clearly some kind of processing is occurring in our visual system that allows us to group these lines and these surfaces in ways so that we can identify which one of them is a 3D object and which one of them is not a 3D object. Clearly this processing is not completely definitive in that sometimes there is ambiguity. You might come up with one answer to this and someone else may come up with a slightly different answer to this because the processing leaves room for ambiguity. To look more deeply into the processing that might be occurring in our visual system that allows us to identify which objects are 3D objects and which ones are just 2D, let us consider a different example. Shown here are 6 sentences. None of the sentences makes much sense semantically. Nevertheless, some of these sentences are grammatically correct, and you and I can quickly detect which of these sentences are grammatically correct. Can you identify which of these sentences are grammatically correct? Which ones did you think, David?
So the first sentence, colorless green ideas sleep furiously, I recognize pretty quickly as a pretty famous example proposed by Noam Chomsky of how sentences can be semantically nonsensical but still grammatically correct. The sentence makes sense, there's still a subject, a verb, an adverb describing the verb, but the idea of a colorless green idea makes no sense. The idea of ideas sleeping makes maybe a little bit of sense. The idea of sleeping furiously is kind of nonsense, so the sentence really doesn't have much meaning even though it's grammatically correct. The second sentence, soft drinks due from Thank Bill's Insurance, really doesn't make any grammatical sense. It does have a seeming subject and a seeming verb, but the verb comes right after a preposition suggesting that the verb fills in the slot proposed by the preposition, which doesn't make any sense. So this one doesn't make any grammatical sense to me. The same can be said for the other 2 negative examples. They don't really have the normal subject-predicate sentence structure, or they have other rules or constraints that are being violated. For the other 2 positive examples, they still maintain this subject-verb sentence structure. So here we have Waldcore notifies, which doesn't make sense, but it matches our structure. And here we have Tuesday brought something, which also makes no semantic sense, but can still be thought of as grammatically correct. Similarly, Tuesday bringing something does make some sense, but a sharp-edged sweet of pumpernickel makes no sense whatsoever.
Note the vocabulary that David used in trying to find out which of these sentences were grammatically correct. It seemed to me that he was examining if the structure of these sentences was fulfilling certain conditions or fulfilling certain constraints that he expects from his knowledge of English language grammar. One could even say that he was doing constraint processing. This brings us to the definition of constraint propagation. Constraint propagation is a method of inference that assigns values to variables, characterizing a problem in such a way that some conditions are satisfied. So if you have any problem, that problem is going to be characterized by some variables, and the task is to give specific values to each variable in such a way that some global constraints are being satisfied. So given a problem, so problems are characterized by a set of variables. Each variable may locally take on some value. However, the question is, how can we locally assign values to variables in such a way that some global constraints are satisfied? As an example, let us return to this figure. Here is a figure drawn on a 2D surface, and the problem is whether or not it represents a 3D object. The variables here are the surfaces and the orientations. One could consider this to be a single two-dimensional surface with some lines drawn on it. Alternatively, one can think of this as having 4 surfaces, 1, 2, 3, 4, where each surface has a particular orientation. The orientation can be specified by the perpendicular to that surface. The method of constraint propagation is going to help identify the surfaces and their orientations. The constraints here are defined by these junctions. For trihedral objects, where 3 surfaces meet at a particular point, these junctions have certain properties. No matter how we assign the surfaces and the orientations, the assignment must satisfy all of those constraints. We'll look at the details of constraint propagation in a minute. But first, notice that there are 2 possible interpretations to this particular 3D object. One can look at it as if one were looking inside a box. Alternatively, one can look at it as if one were looking at a building. This means that constraint propagation need not necessarily always succeed in disambiguating between different kinds of assignments of surfaces and the orientations. Sometimes multiple interpretations can simultaneously satisfy all the constraints. It is also possible that no assignment of values to the variables will satisfy all the constraints, in which case the interpretation becomes very difficult. As another example, let us examine this sentence, "Colorless green ideas sleep furiously." All of us can recognize that this is semantically meaningless, but grammatically correct. How did we know that this is grammatically correct? The variables here are the various lexical categories, like verbs and nouns and subjects and predicates. The values are the assignments we make to these various words here. Is green a noun? Is green a verb? Is green a determiner? Is it part of a subject or part of a predicate? The constraints here are defined by the rules of English language grammar. As we assign values to the various variables here, that assignment must satisfy the constraints of the English language grammar, so that as we assign values to these variables, those assignments must satisfy the constraints of the English language grammar before we can accept this sentence to be grammatically correct. If this sentence was grammatically not correct, then we will not be able to assign values to all the variables in a way that will satisfy the constraints imposed by the English language grammar.
So we've actually come across this idea of constraints in English language grammar before. During our lesson on understanding, we talked about how a preposition, for example, can constrain the meaning of the word that follows it. If we see the word from, for example, we expect what comes after it to be some kind of source for the sentence. There we used grammatical constraints in service of some kind of semantic analysis. Here, we're just using grammatical constraints to figure out if a sentence is grammatically correct or not. There's another connection here to understanding as well. Ashok talked about how we can interpret this shape as either popping out towards us or down into the screen. We talked about 2 simultaneously accurate interpretations of the same thing in understanding, with regard to sentences that can be read as puns. So for example, when I said, "It's hard to explain puns to kleptomaniacs because they always take things literally," the word take can simultaneously be interpreted as interpret and physically remove, while satisfying all the constraints of the sentence.
Let us look at the details of constraint propagation. To do so, we'll take a specific example from computer vision. Here is an example of a 2D image composed of a large number of pixels. The grayness at any one pixel is a depiction of the intensity of light at that pixel. Now, of course, you and I can immediately recognize that this is a cube. But how do we do it, and how can we make a machine do it? Marr decomposed the task of 3D object recognition into several subtasks. Marr said that in the first subtask, the visual system detects edges or lines as shown here. At this particular point, no surfaces have been detected. At this particular point, no 3D object has been recognized. Just these pixels have been grouped into lines based on the intensities of light at the different pixels. According to Marr, the second subtask of object recognition consists of grouping these lines into surfaces with orientations as indicated here. So now these 4 lines have been grouped into the surface with an orientation defined by the perpendicular to the surface. And similarly, these 4 lines and these 4 lines. In the third and final phase of the object recognition task, according to Marr, surfaces are grouped into a complete 3D object. At this particular point, the visual system recognizes that this is a cube. Marr's theory has been very influential in computer vision. It has actually also been influential in AI as a whole. One of the lessons we can take away from Marr's theory of computer vision, of object recognition, is that before we get into algorithms for addressing a task, we want to understand how a task gets decomposed into subtasks. Throughout this course, we have emphasized task decomposition repeatedly. As an example, when we were talking about understanding, the big task of understanding got decomposed into a series of small tasks, where surface level cues acted as probes into memory and a frame was retrieved. The slots of the frames generated expectations. Lexical and grammatical analysis led to the identification of objects and predicates that would satisfy those expectations, and the fillers were put in. Problem reduction certainly is a general purpose method for decomposing complex tasks into smaller tasks. This notion of task decomposition is a powerful idea irrespective of what algorithm we use for any of these specific subtasks. Of course, our focus here is on constraint propagation, not on computer vision. We are simply using some aspects of computer vision to illustrate constraint propagation. In particular, let us zoom into a specific subtask of object recognition. In this subtask, the lines are grouped into surfaces and the orientations of those surfaces are identified via their perpendiculars. The method we'll use for this task is called line labeling. The method of line labeling makes extensive use of constraints. To illustrate the notion of constraints, consider this cube again. You'll notice this cube has junctions, and these junctions have different kind of shapes. For example, this looks like a Y junction. This looks like an L junction. This also looks like an L junction. It's just that this arm of the L is coming in the other direction. This also looks like an L junction. This junction, on the other hand, looks a little bit like a W junction. So junctions of various kinds. Here are the kind of junctions that can occur in the world of trihedral objects like cubes. Y junction, W junction, T junction, L junction. We can say a little bit more about each of these junctions. Let us look at the Y junction first. If we examine the various kinds of Y junctions that get formed in the world of trihedral objects, and we find that whenever there is a Y junction formed, then each of these lines represents a fold, where a fold is a line where two surfaces meet. Now, the important thing about this is that if we can infer that this is a Y junction and that this line represents a fold, then it immediately follows that this line must also represent a fold and this line must also represent a fold. Actually, I should tell you quickly that in the world of trihedral objects, Y junctions can have multiple kind of constraints, but right now let's just look at this one single constraint. Similar in the case of an L junction, which has a shape like this, in the world of trihedral objects, an L junction is characterized by this being a blade and this being a blade, where a blade is a line where we cannot infer that two surfaces are getting connected with each other. Again, the L constraint can actually have many more formulations, but right now we are keeping it simple, just looking at one single constraint for the L junction. Similarly, in the world of trihedral objects, one of the ways in which the W junction gets characterized is through a blade, fold, blade. In effect, we are defining a spatial grammar here for the world of trihedral objects. The equivalent of this in case of grammar of natural language sentences might be that a sentence can have a noun phrase followed by the verb phrase followed by a prepositional phrase and so on. Given this set of very simple constraints for the world of trihedral objects, let us see how these constraints actually can be propagated to group edges into surfaces. Let us do an exercise together. Here is a cube with its 7 junctions. For each of these junctions, identify the kind of junction that it is. What did you write down, David?
So going around the outside, we have alternating L and W junctions, an L in the bottom left, a W, an L, and so on. Right in the center, we have a Y. So we can differentiate a Y junction and a W junction by saying that for a W junction, one of the 3 angles has to be over 180 degrees, whereas in a Y junction, all 3 are less than 180 degrees. A T junction happens when one of the angles is exactly 180 degrees.
This sounds good, and now let us look at how we'll apply these constraints to identify the surfaces. Let us do another exercise together. We have identified the type of each of these junctions. Let us now use the constraints for each type of junction to identify the type of each of these edges. For each of these boxes, write either fold or blade for the type of the edge. What did you write, David?
So starting in the top left, I used the L junction up here to look at the L constraint, which said that both 5 and 1 are blades. I then used the W junction right here to look at the W constraint and find that these should be labeled as blade, fold, and blade from 1, 2, and 3. I noticed that the L constraint and the W constraint for these 2 junctions both made this edge a blade, and that followed around for the entire figure. Whenever one junction said that a certain edge was of certain type, like blade, all the other junctions that were connected to that edge said the same thing. So in the center, for example, the Y constraint here would say that 2, 6, and 7 are all folds, and indeed 2, 6, and 7 all play the role of folds with regard to the W constraints here, here, and here.
That's good, David. Note that David cited on the top left corner. This was a random selection. He could have cited at any other corner, for example this one or that one, and found the same answer. And that is because we have simplified these constraints. But now that we know that this line is a fold, by the definition of a fold, we know that 2 surfaces must be meeting in this line. It follows then that this must be a surface and this must be a surface. Similarly, because we know this is a fold, and by definition of a fold, 2 surfaces must be meeting here, it follows and this is a surface and this is a surface, and so on. And now we have identified that this is one surface, this is another surface, this is a third surface. In this way, the visual system used knowledge of the different kind of junctions in the world of trihedral objects and the constraints at each of those junctions to figure out which of these lines made surfaces. Instead of thinking of this as one single surface, the visual system identified this as being composed of 3 different surfaces, and now we can recognize that this might be a cube. Now that we have discussed constraint propagation technique, David, why do you think you did not see this as a 3D object?
So I think there's 2 reasons, actually. The first reason is that there's a junction right here that I just don't have in my dictionary of junctions. It involves 4 lines coming together at a point, but I can't deal with anything more than 3 at a Y constraint. So the fact that I don't see this as a junction makes me not naturally see that as any kind of realistic shape. The other is that if I label these 3 intersections with their junctions, I'll get an L, a Y, and an L. If I propagate the constraint from the L junction, I see this is a blade, and this is a blade. If I propagate it from the Y junction, I see these are all 3 folds. But now I have the Y junction telling me that this is a fold, and the L junction telling me that this is a blade. So I have a conflict in my attempt to propagate my constraints down onto this shape. And the result, I guess, is that I don't see it as a shape, because it doesn't fit my constraints.
Now, of course, some of us do see this as a 3D shape. You can think of this as a paper folded here, one plane of the paper and another plane of the paper. This looks kind of like an open book. This particular line here then can be ignored, it just being a line on the 2 planes, not signifying a surface by itself. If we view this only as a line and not signifying a surface, then that addresses David's first problem. But how do we address David's second problem of this being a fold or a blade, depending upon where we start the constraint propagation from? The answer is that we actually have a much more complex ontology of these connections. The answer lies in the fact that we have so far used a very simple ontology just to demonstrate the constraint propagation process. In reality, the ontology of these constraints is more complicated. Thus, the Y constraint may not just have fold, fold, and fold, but it might also be blade, blade, and blade. And the L constraint is not always blade, and fold, and fold, but it could also be blade, and fold, and fold, and blade. Now we can see David's second problem disappearing because the Y junction may have a blade and the L junction may also suggest a blade, and there is then no conflict. Let me note that what we have shown here is still not a full ontology of the Y, W, L, and T constraints. T constraints in particular may have additional complexity. The advantage of having a more complete ontology is that we can use that ontology to interpret more complex scenes, like this one, where there are two rectangular objects, one being partially occluded by the other one. Of course, the more complicated ontology is not without its own problems. It now introduces ambiguities of a different kind. This particular junction, is it now a blade, 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 or is it a fold, fold, fold? Both of them are permissible in the new complete ontology. In order to resolve some of these ambiguities, we can come up with additional conventions. One convention is that all of these edges that are next to the background, we'll consider them to be blades. So we'll make this a blade, 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 blade. Once you make all of these blades, then it's easy to propagate the constraints. Thus, this W junction could have been a fold, blade, fold, or a blade, fold, blade. But if we adopt the convention of labeling all of these lines as blades, then this W junction can only be blade, fold, blade. But if this is a fold, this Y junction can only be fold, 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 and so on, and that helps us resolve the ambiguity of what this junction could be. This task of image interpretation is an instance of the abduction task. In abduction, we try to come up with the best explanation for the data. This is the data, we're trying to interpret it in terms of an explanation. We'll discuss abduction in more detail when we come to diagnosis. For now, notice that we start with what we know, blade, 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 and then we propagate the constraints so that we can disambiguate between other junctions. Let us again return to this sentence, colorless green ideas sleep furiously. You and I can quickly recognize that this sentence is grammatically correct even as it is semantically meaningless. How do we do it? Consider this mini grammar. This is a small subset of the English language grammar consisting of just 3 simple rules. This sentence can go into a noun phrase followed by a verb phrase. A noun phrase can be optional adjectives followed by a noun or a pronoun. The square bracket here means optional. A verb phrase is composed of a verb followed by optional adverb. The variables in this particular sentence are the words. The values we assign to them are the lexical categories like verb, adjective, noun, and pronoun. If we can make a parse tree for this, that assigns values to these variables in a way that is consistent with this grammar, then this particular sentence is grammatically correct. Let us try to make a parse tree for this sentence. A sentence can be a noun phrase or a verb phrase. So we may say that this is a noun phrase and this is a verb phrase. Of course, at this particular point, we do not know where we should make this demarcation, what should go into the noun phrase, what should go into the verb phrase. We'll know whether or not this demarcation is correct depending upon whether or not this noun phrase and verb phrase meet the lower level lexical categories. So let us look at colorless green ideas. We know that a noun phrase can go into one or more adjectives followed by a noun or a pronoun. So we can look at a lexicon and know that ideas are a noun. So we say this is a noun. We can look at a lexicon that tells us that colorless and green are adjectives, and so colorless and green are adjectives here. We have satisfied this part of the constraint. Similarly, for the verb phrase, a verb phrase can be composed of a verb followed by one or more optional adverbs. We can look at a lexicon and sleep is a verb, and furiously is an adverb, so we have satisfied the constraints for this particular part. Because we have satisfied the constraints, we know the top level demarcation of this as a noun phrase and this as a verb phrase was correct. So the processing is not only top down here, it also has a bottom up component. In this way, we are able to decide that this particular sentence is grammatically correct because it satisfied the constraints of a mini grammar. Note that we have used knowledge of constraints in the method of constraint propagation, both for visual processing and for language processing. Thus, this method is very general purpose and domain independent. Once we have done constraint propagation to derive the parse tree for this sentence, then we can do additional processing. We can use this parse tree to support semantic analysis to build an understanding, a semantic understanding of the sentence. Similarly, in visual processing, once we have used the constraints for doing line labeling and recognize the surfaces and their orientations, we can then go on further and recognize the object in its 3D form.
So how would constraint propagation be useful for Raven's progressive matrices? This concept has a strong correspondence to the final project, where you'll be asked to reason over the images of the problem directly instead of over the propositional representations that we've given you in the past. So first, if constraint propagation leverages a library of primitive constraints, what will your constraints be for the final project? How will you propagate those constraints into the image to understand it? Then, once you actually propagated those constraints, how will you actually use those inferences? Will you abstract out propositional representations, or will you stick to the visual reasoning and transfer the results directly? So today we've talked about constraint propagation, which is a method of inference where we assign values to variables to satisfy certain external constraints. By doing so, we arrive at strong inferences about the problem, like which shapes represent objects or how the words in a sentence interact. After defining constraint propagation, we talked about how it can be useful in interpreting images by using prior knowledge of constraints to anticipate predictable shapes out in the world. Then we talked about natural language understanding, where prior knowledge of the rules of grammar and the parts of speech allow us to make sense of new sentences. Now, constraint propagation is actually an incredibly complex process. We have numerous constraints for visual scenes and verbal sentences that we haven't discussed here. We also use constraint propagation in other areas as well, such as in making sense of auditory and tactile information. Reading Braille, for instance, can be seen as an instance of constraint propagation. We'll pick up on this discussion later when we talk about visuospatial reasoning, but this will also come up in our discussion of configuration, which can be seen as a specific instance of constraint propagation in the context of design.
Constraint propagation also connects to human cognition. First, constraint propagation is a very general-purpose method like mean-sense analysis. In both knowledge-based AI and in human cognition, constraint propagation allows us to use our knowledge of the world in order to make sense of it. Constraints can be of many kinds, symbolic as well as numeric. We discussed symbolic constraints in today's lesson. A good example of numeric constraints comes from Excel spreadsheets with which most of you are familiar. If the columns in a particular spreadsheet are connected through some formula, and you make a change in one column, then the change is propagated into all the columns of the spreadsheet. That's an example of numerical constraint propagation. We have seen constraint propagation under other topics as well, for example, planning and understanding and scripts. The next topic, configuration, will build on this notion of constraint propagation.
All right, please write down what you understood from this lesson in the box right here.
And thank you for doing it.